Lesson 11. Chemical bonding. Objectives. Learn about ionic and covalent bonds and explain how they are formed. Learn about the polar covalent bond. Understand the nature of bonds and their relationship to electronegativity. Understand bond polarity and how it is related to molecular polarity. Learn about stable electron configuration. Learn to predict the formulas of ionic compounds. Learn about ionic structures. Understand factors governing ionic size. Learn to write Lewis structures. Learn to write Lewis structures for molecules with multiple bonds. Understand molecular structure and bond angles. Learn to predict molecular geometry from the number of electron pairs. Learn to apply the Vesper model to molecules with double bonds. Introduction. Atoms rarely exist alone in nature. Instead, they combine with other atoms to form molecules and ionic compounds. Chemical bonding explains why atoms bond, how they bond, and what properties result from those bonds. Understanding bonding is essential for predicting the formulas, shapes, polarity, and reactivity of substances. 1. Ionic and covalent bonds. Ionic bonds. Formed when electrons are transferred from one atom to another. Typically occur between a metal and a nonmetal. Result in ions. Cations plus lose electrons. Anions gain electrons. Oppositely charged ions attract via electrostatic forces. Example.
Sodium loses one electron and form a cation. Chlorine gains one electron and produces an anion. Together, the cation and the anion makes an ionic compound that generally are solid that conduct electricity, solid that in solutions conduct electricity, and also when the solid is melted.
No molecules or formed ionic compounds form crystal lattices.
What about the covalent bonds?
Covalent bonds. Formed when atoms share electrons. Usually occur between nonmetals. The shared electrons allow atoms to reach stable configurations. Example. H2, each hydrogen shares one electron. H2O, oxygen shares electrons with two hydrogens. 2 polar and nonpolar covalent bonds. Electronegativity, En.
Okay, let's see. The electronegativity is the ability of one atom to attract the electrons in the bond. The electronegativity increases across the period to the right and in the group up. Increases when you are going up and decreases when you are going down. So the orange elements, nitrogen, oxygen, fluorine, and chlorine, have electronegativities between 3 and 4. Then they are the most electronegativity. In special, fluorine is the most electronegativity element in the periodic table. While this one in violet are the metals and are the less electronegativity. Francium, that is supposed to be here down, is the metal that is less electronegativity in all the periodic table. As you can see, here is the less electronegativity, and here is the most electronegativity. Then let's continue.
A measure of an atom's ability to attract electrons. Increases across a period, decreases down a group. En difference. Bond type. 0.
When the difference of electronegativity is 0 or very close to 0, the bond is nonpolar covalent. When the difference is between 0.4 and 1.7, the compound is polar covalent. And when it is higher than 1.7, it is ionic. Some author change this to 1.8, some says that is 2, but more or less this is what we have. Let's see in order that you understand it. For example, you have a compound where you have, for example, a carbon and hydrogen. And you come to the periodic table and you see the electronegativity of carbon is 2.5 and the electronegativity for hydrogen is 2.1. Then the difference is 0.4. As you can see, it is close to 0. Then we consider that this bond between carbon and hydrogen is nonpolar covalent. But suppose that then now you have carbon and, for example, a beryllium. Look at this. In this case, you have 2.5 of carbon minus 1.5 of beryllium, and the difference is 1.0. So, this bond is polar covalent. And now we are going to see the difference between, for example, a fluorine and sodium. Well, fluorine is 4.0 and sodium is 0.9. Then the difference of electronegativity in this case is 3.1. Then this compound, of course, is ionic. This is the way that you can determine the type of bond between two atoms. Let's continue. Then
Electrons are shared unequally. Partial charges are developed. Delta, less electronegative atom. Delta, more electronegative atom. Example: OH bond in water. Oxygen attracts electrons more strongly O delta, H delta. 3. Bond polarity versus molecular polarity. Important distinction. Bond polarity applies to individual bonds. Molecular polarity depends on bond polarity, molecular shape. Examples: CO2, polar bonds, but nonpolar molecule, linear, symmetric. H2O, polar bonds plus bent-shaped polar molecule.
why? Why happened this? Well, okay, we are going to speak about this later. Now, all what I want you to understand is that the shape of the molecule in water is bent, and in carbon dioxide is linear. So this is carbon, one oxygen one side, one oxygen the other side. This is the direction of the dipole in this bond, and this is the direction of the dipole in this bond. As they are equal, but they are in opposite direction, they cancel up, and the net dipole in this molecule is 0, and we consider that the molecule is non-polar. Even though, if you take into account this bond and this bond, they are both polar, but the whole molecules, because of the shape, is non-polar. While in water, well, look at this. You have hydrogen one side and hydrogen the other side. These molecules have a delta positive charge this side and a negative charge this side. And this molecule, because it's bent, you cannot say that is non-polar. It is polar. Then water is a polar molecule. Let's go to the following concept: stable electron configurations.
Stable electron configurations.
Okay, atoms, as you can see,
Atoms bond to achieve stability. Octet rule, atoms tend to have 8 valence electrons. Exceptions. Hydrogen, 2 electrons. Expanded octets, period 3 and beyond. Odd electron species. 5. Predicting formulas of ionic compounds. Rules. Write the ions with charges. Balance total positive and negative charge. Use subscripts, lowest whole number ratio. Example. Al superscript 3 and O superscript 2. LCM of charges equals 6.
Subíndice base al final base.
okay, then in this case, let me show you because here is not very well explained. Aluminum has +3, while oxygen has -2. What we do, we cross these charges, and then we put the 2 into here and the 3 here, and we forget about the sign. Then the formula will be 2. We need 2 aluminum atoms per 3 atoms of oxygen, and this is the formula of the compound in order to get stable compounds. Let's continue. Let's continue now. We are going to see the ionic structures.
Ionic structures. Ionic compounds form 3D crystal lattices, not molecules. High melting points. Conduct electricity when molten or dissolved.
Then you can see here, this is a structure of an ionic compound. As you can see, they make a 3D crystal lattice. You have the chlorides and the sodium cations making this crystal. These compounds have these characteristics. They have high melting points and conduct electricity only when they are melted or they are dissolved. When they are in solution, the ions are free and they conduct electricity. Let's continue. Factors governing the ionic size. Cations are smaller than the parent atoms. For example, let me show you something that you will understand immediately. This is sodium. But when sodium atom loses one electron, the size is smallest because it has one electron less. then the cations are smallest than the parent atom. In the opposite, the anion, if this is the anion and the anion gains 1 or 2 electrons, the anions are larger. This is the anion, for example, Cl negative 1 is larger than the atom chlorine. Here you can see the isoelectronic series example. For example, sodium, the anion oxide is bigger than the anion fluoride, and the anion fluoride is bigger than the sodium cation, and the sodium cation is bigger than magnesium cation. This is the isoelectronic series, or is one of them. This is an example. Let's continue. Let's go to the Lewis structure. This is very important that you understand the representation of the Lewis structure. Let's see it by step.
Lewis structures. Steps. Count total valence electrons. Arrange atoms least electronegative central. Form single bonds. Distribute remaining electrons. Check octets and total electrons.
Okay, let me stop into here. For example, we know that carbon is in the group of carbon, they have 4 valence electrons. Then 1, 2, 3, and 4. I don't begin sharing until I have 4 electrons in each side of the atom. Look at this. In the case of oxygen, this is incorrect. This is incorrect. Let's see how is oxygen. Oxygen has 6 electrons. Then you begin 1, 2, 3, 4, and now you begin pairing 5 and 6. This is the structure or the Lewis representation for the oxygen atom. For chlorine, chlorine has 7 electrons, so you begin 1, 2, 3, 4, 5, 6, 7. As you can see, this atom has 7 electrons or valence electrons. They are the most important in the chemical reactions. But if you go to the noble gases that are in the last column, you can see I'm going to represent, for example, neon. For example, neon has 8 electrons in the outermost shell. 8 valence electrons. Then this configuration is very stable. They don't need electrons, or they don't need to lose electrons to have 8 electrons in the outermost shell. 8 electrons give stability to the atom. Then chlorine, in order to be stable, needs how many electrons? 1 electron. That's why chlorine makes chloride ions with gaining 1 electron. What about oxygen? Oxygen needs 2 electrons. That's why they make the anion oxide with 2 extra electrons. to get the noble gas configuration, in other words, A electrons. Only in the case of helium, helium has the electrons in the first level, in the 1s, and in this level only allows 2 electrons. Then the stability in this case for helium is 2 electrons. Let's continue. For example, here we have for ammonia. Look at this. This is the formula for ammonia, but we know that nitrogen has 5 electrons, valence electron. This is nitrogen, 1, 2, 3, 4, 5. This is nitrogen. Nitrogen has 5 valence electrons, and hydrogen has only 1. But as in the ammonia formula we have 3 hydrogen, we have to multiply by 3. Then how many valence electrons do we have in this compound? 8. Then we put the most electronegative atom in the center, and then we make a bond with hydrogen, 1 hydrogen here, 1 hydrogen here, and 1 hydrogen here. Then I put 2 electrons here to make a simple bond between hydrogen and nitrogen, and the same thing here, and the same thing here. How many electrons do I have in this structure? 6. But how many more we can add? 2 more, because these atoms has 8 valence electrons. Where I put here in hydrogen? No, because hydrogen is good with 2 electrons. This is good with 2 electrons, and this is good with 2 electrons. But what happened with nitrogen? Nitrogen in this case has only 6 electrons, and nitrogen needs 8 electrons. That's why I put the rest 2 electrons here, and this is the electron distribution according with Lewis for this compound. What happened? That this bond that are made of 2 electrons can be represented by lines. And these 2 electrons are not shared with anyone, so they are lone pairs. This is a lone pair. And this is the Lewis structure for ammonia. Well, we have more complicated things. What happened with oxygen? Well, let me go step by step. Look at this. We have 2 atoms of oxygen, and we make a bond in between. But we know that every atom of oxygen has 6 electrons. Then we have 6 and 6, 12 electrons. Then I have 2 here, then I continue here, 4, 6, 4, and 6, then 1, 2, 3, 4, 5 times 2 is 10. Then I have 2 more electrons to complete. But what happened here? That this atom has only 8 electrons. That's perfect. That's a noble gas configuration. But what happened with the other one? Oh, it only has a 6. Then it doesn't, it is not satisfied. it is not satisfied because it cannot make the octet. Then how we can do this in order that both will be satisfied? Well, if I put these two electrons here in between and I make a double bond in between, then this atom will have these electrons and this will have these electrons, and then here I will have 2 and 2, 4 and 2, 6 and 2, 8 and 2, 10 and 2, 12. Then making a double bond, now this atom has 8 electrons and this has 8 electrons, and both are good with the octet rule. Then you can go now to explain the same thing with nitrogen. With nitrogen, you make a triple bond. If you go step by step, you will see that the triple bond will satisfy both atoms, because 2, 2, and 2, and 2 is 8, and 2, 2, 2, and 2 is also 8. Then both are good with the octet rule. In this case, we can explain the same thing by using the carbon dioxide molecule. And this way you can see that this compound will be linear. Let's go. Now let's see the repulsion between pairs of electrons, and one theory that explains the how to lower the repulsion between the electron pairs. You can get different geometries in the molecule. For example, if you have two pairs of electrons, two groups of electrons, the molecule will be linear like carbon dioxide, and the bond angle will be 180. If you have three pairs of electron groups, then the molecule will be trigonal planar. Look, like this one. This is linear, but this is trigonal planar because it's a triangle in the same plane. And if you have three, but they are disposed in this way, this is also trigonal planar, but in this case you have a lone pair of atoms because these two electrons belongs only to sulfur. Then we say that this pair is non-shared. In the case of carbon and hydrogen, methane in this case, is tetrahedral because you make 4 bonds and every bond is 109.5. In the case of ammonia, you have a lone pair, but you have also is tetrahedral because it has 1, 2, 3, 4 pairs of electrons, and one pair is non-bond. Then here we have water that is also tetrahedral. But what happened that in the case of carbon dioxide is linear, but SO3 is trigonal planar. In the case of of CH4 is tetrahedral, but in the case of water is bent. Okay? And also is bent for this compound. Here is also bent, as you can see. All right, all right, all right. Let's continue. Let's continue. Here you have the different angles. And let's speak a little more about the theory that explains the geometry of the molecules. The VSEPR, that is the valence shell electron pair repulsion, the one that explains how the electrons are supposed to be far one from the others in order to lower the repulsion. Let's go to the different steps and you will understand it better. Lexi.
Steps. Count electron domains. Determine electron geometry. Adjust for lone pairs molecular geometry. Vesper with double bonds. Double bonds count as one electron domain. They repel slightly more than single bonds. Example. CO2, 2 domains linear. C2H4, trigonal planar around each carbon. Vesper example explained, step by step. Vesper equals valence shell electron pair repulsion. Key idea, electron pairs around a central atom repel each other and arrange themselves as far apart as possible to minimize repulsion. This determines the shape of the molecule. Step 1, draw the Lewis structure. Oxygen, O, has 6 valence electrons. Each hydrogen, H, has 1 valence electron. Total equals 6 plus 2 is equal to 8 valence electrons. Lewis structure. O is the central atom. 2 OOH single bonds. 2 lone pairs remain on oxygen. Step 2, count electron domains. Electron domains equals regions of electron density. 2 bonding pairs, OOH bonds. 2 lone pairs. Right arrow total equals 4 electron domains. Step 3, determine electron geometry. For electron domains, tetrahedral electron geometry. Ideal angle equals 109.5 degrees. This describes the arrangement of all electron pairs, not just atoms. Step 4, determine molecular geometry. Now ignore lone pairs and look only at atoms. 2 bonded atoms. Molecular geometry equals bent angular. Step 5, explain the bond angle. Lone pairs repel more strongly than bonding pairs. They push the OOH bonds closer together. Heavy checkmark actual H-OOH angle is almost equal to 104.5 degrees, not 109.5 degrees. Why Vesper works here? Electron pairs repel each other. Lone pair repulsion, lone pair, a bond, bond, bond. Shape adjusts to minimize repulsion. Quick comparison example, CO2.
Look at here. You have carbon dioxide. The central atom is carbon. Then you share the electrons as I showed you before. You made the double bond in order to explain that every atom is okay with the octet rule. And then you go to the table and you say, well, if I have 2 groups of electrons and the central atom has not lone pairs, then if you go to the table, you can see that 2 pairs of electrons and no lone pair, the geometry is linear. So carbon dioxide is a linear molecule. Understand? And the angle bond is 180. Okay? Let's go now.
One sentence summary for students. Vesper predicts molecular shape by assuming that electron pairs around a central atom repel each other and arrange themselves as far apart as possible. Tricky questions, assessment style. 1. Which compound has polar bonds but is nonpolar overall?
Okay, look at this. Water has polar bonds and is polar because it's bent, as I told you before. This is water. Water is bent. It's polar because in the oxygen you have the negative charge and the hydrogen has a delta positive charge. Ammonia. Oh, what is the problem with ammonia? Ammonia has a lone pair of electrons, and this will give a delta negative charge this side. Then it's also polar. What about SO2? You have S, you have the oxygen, both sides, and you have in SO2 is also polar because you have lone pairs. So it is not linear. But what happened in carbon dioxide? That you have double bonds and is linear, so this dipole is cancelled with this one because they are equal and in opposite directions. Then the net polarity of this compound is 0. Then the only compound that is non-polar overall is CO2. Why is sodium chloride not considered a molecule? Oh, because it forms an extended ionic lattice, no discrete particles, and it is made of ions, and the ions, the cation and the anion make a lattice that is ionic. Which ion is the largest? Oh, remember that between these four that you see here, we have here a series. You remember the series that we were talking about? Let me go back in order that you can remember what I'm talking about. Look, this is an isoelectronic series example. The largest one, the biggest one is oxygen, and magnesium is the smallest one. So we can go down again and answer this question. Which one is the largest? Oxygen. Remember, the anions gains electron, they get, then the radius is largest. They are bigger. Why does NH3 ammonia have a smaller bond angle than CH4? Oh, because CH4 is tetrahedral, but ammonia has a lone pair here and is pyramidal. All right? Then the bond here is smaller than here. And here you have more questions. In the case of carbon dioxide, you know why the molecule is not polar is because of the linear geometry and the dipoles are canceled. Well, let's go to the end of this chapter and we are going to see some important things.
Key takeaway. Chemical bonding connects electron behavior to the structure, shape, and properties of matter. Mastery of bonding allows you to predict formulas, polarity, geometry, and chemical behavior, core skills for all future chemistry topics. Water, the importance of a geometrical structure. Water is chemically simple, just two hydrogen atoms bonded to one oxygen atom, yet it behaves in ways that make it exceptional among molecules and essential for life on Earth. Let's explore how it's similar to other molecules, and then why its unique properties make it a life-saving substance. How water is similar to other molecules. Made of atoms bonded by electrons, like other molecules, water forms covalent bonds. Electrons are shared between atoms. Has a molecular shape. Water has a bent shape due to electron repulsion, just like other molecules shaped by Vesper theory. Can exist in all three states: solid, ice, liquid, water, and gas, steam, like many other substances. Undergoes phase changes. Water melts, boils, condenses, and freezes like other molecular compounds. What makes water special? 1. High specific heat capacity. Water requires a lot of energy to change its temperature. This stabilizes climates, regulates body temperature, and buffers ecosystems. Oceans absorb solar energy without overheating, keeping Earth's temperature moderate. 2. Polarity and hydrogen bonding. Water is a polar molecule. Oxygen pulls electrons more strongly than hydrogen. This polarity allows water molecules to form hydrogen bonds with each other. Result: cohesion, surface tension, and a high boiling point. 3. Universal solvent. Water dissolves more substances than any other liquid. It carries nutrients, minerals, and gases in biological systems and ecosystems. 4. Density anomaly of ice. Ice is less dense than liquid water due to hydrogen bonding, forming a crystalline structure. Ice floats, insulating lakes and oceans from freezing solid, protecting aquatic life. 5. Capillary action. Water climbs narrow tubes against gravity due to cohesion and adhesion. This enables water transport in plants from roots to leaves. How water saves life on Earth. Climate regulation. Oceans and lakes absorb heat, preventing extreme temperature swings. Cellular stability. Water buffers pH, transports nutrients, and enables biochemical reactions. Protection from freezing. Floating ice insulates aquatic environments. Hydration and cooling. Sweating and evaporation help regulate body temperature. Tricky question. True or false? Water heats up quickly, making it ideal for regulating body temperature. Answer: false. Why? Water heats up slowly due to its high specific heat, which helps stabilize temperature.
Okay, now you can answer all these questions because I gave you a lot of information about the importance of water, and without water, for sure, there wasn't life in Earth. Well, see you in the next video. Bye.